Hello students, welcome to Inside Physics. Today we will see what is Gauss law in electrostatics. Okay, see before going to Gauss law, we will see what is electric flux first of all. See, what is electric flux? The number of lines of force of electric field passing through a given area perpendicular to that area is called electric flux. It is denoted by phi. Electric flux is denoted by phi. So this electric flux is because of the charge, and the charge generates some electric lines of force. Those electric lines of force which are passing through a given area is called electric flux, and this flux should be perpendicular to that given area. Next, we will see what is Gauss law or Gauss theorem. See, Gauss law says the total electric flux coming out of a given surface area is equal to the charge enclosed by that surface by epsilon naught. See, the total electrical flux through a given surface area, and a charge is enclosed in that surface area. So in mathematical form, the Gauss theorem can be represented as E bar dot ds bar is equal to q by epsilon naught. So this is the mathematical form of Gauss law. This circle represents that the bounded surface, that is called Gaussian surface, should be a closed one, and the charge present inside the closed surface is q. So here the Gauss law has many advantages. Here we can find the electric intensity and the electric potential of a different charge conductors. So by taking some Gaussian surface around them, and the Gauss law is applicable for both static and moving charges also. Okay. So here this is the mathematical form of Gauss law, and now we will see two applications where we can find the electric intensity of some charged conductors by Gauss theorem. Okay. See, first, electric intensity due to a long infinite charged wire. Okay, electric intensity due to a long infinite charged wire. This intensity we can find with the help of Gauss law. Okay, see, first we will take a long conducting wire which is having positive charge around it. Okay, which is having positive charge around it. So we imagine a cylindrical surface around this infinite charged conducting wire. To calculate the electric flux coming out of that closed cylindrical surface, which we will take around this wire. Okay, now we take a closed cylinder around this wire. Okay, which is having a length L. Okay, AB CD is the closed cylindrical surface around this positively charged conducting wire. See, the length of the cylinder will be R, and the flux coming out of this charge enclosed by this cylinder will be radially outward from this surface, okay, in this direction. So the flux coming through the surfaces AB and CD will be 0, because see, if it is a surface we will take as ds2, and if it is a ds1, okay. So here E ds1 is equal to E bar E ds2 is equal to 0, because the surface here is perpendicular to the electric field, okay, and this surface is also perpendicular to this surface, okay. While this surface is perpendicular to this surface, this is also perpendicular to electric field, okay. So in this way we can say the flux coming out of from this surface and this surface will be 0. The flux will only be coming out from this surface and this surface, okay. Now we will see, calculate the total flux coming out of this entire cylinder with some Gauss theorem, okay. Now we will take that E bar dot ds bar is equal to Q by epsilon naught, right. See here, the total surface, right, with this integration we can write S is equal to Q by epsilon naught. See here, the charge distribution, the charge density across this cylinder will be lambda. The charge density will be lambda, and the length of the cylinder is L. So here we can write Q as lambda into L by epsilon naught. Here what is the entire surface? How we can get the entire surface of the cylinder? See here, E bar dot 2 pi R into L, 2 pi RL. R is the distance from this charged conducting wire to the cylinder. So this is the radial distance of the cylinder, which is R, represented with R, okay. So here this will be equal to lambda L into epsilon naught, right. So by this we can write E is equal to, so L will be getting cancelled, lambda by 2 pi epsilon naught R. So this will be the electric intensity because of this Gaussian surface coming out of this Gaussian surface due to the charge enclosed in this cylinder, okay. So by this way we can calculate the electric intensity of the enclosed charge, okay. This is how we calculate electric intensity coming out of the total surface enclosed by this charge, and this is due to a long conducting wire, okay. See next we will see the electric intensity due to a infinite conducting sheet, infinite charged sheet, okay. due to a the electric intensity due to a infinite long charged sheet. Okay, this is the second application by which we can find the electric flux due to a infinite long charged sheet. Suppose if we consider a long infinite sheet with some boundaries P, Q, R, S. See, these boundaries does not reflect any finite length. So, this just for our consideration, we will take this finite sheet as PQ with boundaries PQ, RS. Okay. See, in this sheet, again we will take a Gaussian surface in the form of a cylinder. Okay, horizontal cylinder. That means, see, a horizontal cylinder. Okay, here the horizontal cylinder is going through the sheet. Okay, see, the distance from this sheet on the left side and the right side of the cylinder will be equal. Okay, see, here the electric field will be coming in this direction and the electric flux perpendicular to this surface, if this is called ds, and this surface we can take it as ds1, this is ds2, a small surface we will consider. After that we will integrate with for that surface to get the total electrical flux. Okay, so here the distance of the cylinder will be 2r. Okay, the distance of the cylinder will be 2r from here to here. That means that left side of the cylinder and right side of the cylinder are equal lengthed from the sheet. Okay, so here what should we do to calculate the entire flux coming out of this Gaussian surface? If you imagine this is a Gaussian surface, in this way, see, here also the electric flux coming through this surface ds3 and ds4 will be 0, because if we consider a small surface area here, this surface area will be perpendicular to this surface area and the electric flux coming out of in this direction will be coming from these surfaces. Okay, and this is perpendicularly and this is also perpendicular to this surface, so this is also perpendicular to the electric field. So in this way we can say is equal to 0. Okay, so here again we apply the Gauss theorem to this Gaussian surface in the form of which is in the form of a cylinder. We take the Gaussian formula is equal to q by epsilon naught. So this entire sheet, infinite sheet, is having a charge density of sigma, having a charge density of sigma. So here we can write q, this charge density into the surface. This is the surface which is having a small surface area ds1, so the total surface area is s. Okay, so here we can say that sigma into surface area by epsilon naught. So take it, this one, take the left side part. Okay, so here dot ds bar is equal to sigma s by epsilon naught. So if we integrate this one, we will get es is equal to sigma s by epsilon naught. So here s gets cancelled, so the electric field will become, here see there are surfaces, two surfaces are there which are coming the electric flux through two given surfaces, right? So here we can take that the surfaces as s plus s is equal to 2s. That means we can write here into 2s is equal to sigma s by epsilon naught. So that implies E will become electric field, electric intensity will become S will get cancelled by 2 epsilon naught. Okay, this is the electric intensity due to a infinite long charged sheet. The intensity will be due to the charge enclosed in this Gaussian surface. Okay, so in this way we can do some applications of Gauss law, and we can find the electric intensity. Here we find the intensity, and we can find the potential also with different charged bodies. And here in to apply Gauss law, the surface should be a closed one, and it cannot be of any shape, irregular or irregular, and the charge inside the Gaussian surface can be anywhere inside the surface. So in this way the Gauss law has more applications in electrostatics. So in next class we will see some more applications of Gauss law.